There's this strange idea that sometimes the hardest problems have the simplest, most elegant solutions. Well, it turns out in the world of AI, that's not just a nice thought, it might actually be a mathematical reality. We're going to dive into a paper that suggests a truly fascinating paradox, that some AI problems get faster to solve the harder they get.
So, let's talk about diffusion models. These things are the wizards behind today's generative AI, turning what is literally just random static into these incredible photorealistic images. They work step by step, carefully cleaning up the noise until a perfect picture emerges. But here's the catch: every single one of those steps is computationally heavy. It's slow. And that slowness, that bottleneck, is the exact problem we're here to unpack.
All right, to really get a grip on this, we need to know the lingo. The key metric everyone in the field cares about is the number of function evaluations, or NFE. Just think of it like this. Each step in that denoising process makes the AI model do a function evaluation. So, more steps, more NFEs. More NFEs means more time, more compute power, and, yeah, more money. The name of the game is simple. Get amazing images with the lowest NFE you possibly can.
Okay, so let's break it down. Where does all that cost actually come from? Why is this step-by-step process so demanding? Well, it turns out that the final error, the gap between a perfect image and what the AI spits out, it actually comes from two totally different places.
So you're basically fighting a war on two fronts. On one side, you have discretization error. See, the ideal way to denoise an image would be a perfectly smooth, continuous process, but computers don't work that way. They have to take tiny little discrete steps, and each of those steps is just an approximation, so tiny errors build up. To fight that error, you have to take more and more steps, which costs more. Then on the other side of the battlefield, you have approximation error. This one's all about the AI model itself. The U-net we use is just our best guess at some perfect God-tier mathematical function that could denoise an image flawlessly. A bigger, beefier model gets you closer to that perfection, but guess what? A bigger model costs more to run on every single one of those steps.
And here's where it gets really interesting. Researchers found this scaling law that connects the model's size to its accuracy, and it's brutal. To make your model just a little bit better, say to cut the error in half, you have to make the model exponentially larger. This relationship is measured by an exponent they call gamma. A high gamma means you've got a really hard problem on your hands, because you have to pour in tons of resources just to get a tiny bit better. And this gamma, well, it's the key to this whole story.
So traditionally, you couldn't separate these two costs. They were just tangled together. If you wanted to get your total error, which we'll call epsilon, down to some target level, you had to pay up. You paid the price for taking more steps, and you pay the price for using a bigger model. This gives you a combined cost that scales really, really poorly. For a long time, this looked like a fundamental law of physics for diffusion models, an unbreakable speed limit.
But this is where the script flips completely. What if the very thing that makes the problem so hard, that really high gamma value, is actually the secret to making it faster? What if, in a crazy paradox, a harder problem was actually easier to solve?
And that brings us to this idea of the harder than Monte Carlo regime, or HTMC. A problem officially enters this club when its scaling exponent, gamma, is greater than 2. So what does that actually mean? It means the problem is so dominated by the approximation error, the cost of the model itself, that the other error, the one from taking discrete steps, becomes almost irrelevant. The sheer size and cost of the AI model is now the one and only bottleneck that matters.
So, the million-dollar question is, are our image generation models actually in this HTMC regime? Well, the paper's authors ran the numbers. And take a look at this. For generating these 64 by 64 Celeb A images, they measured a gamma of about 2.5. That is well over the HTMC threshold of 2.0. So this isn't just some abstract theory. The real-world problem we're trying to solve is officially harder than Monte Carlo.
Now that we know the problem is in this special regime, we can finally talk about the solution that takes advantage of it. It's called the multi-level Euler-Murayama method, or MLEM for short. And honestly, it is one of the cleverest things I've seen in a while.
Okay, the idea behind MLME is just brilliant. Instead of having one giant, expensive model do all the work, you use a whole team. You have a bunch of models, from tiny, cheap, fast ones all the way up to your big, accurate, expensive one. And here's the trick. At every single step, you always use the cheapest, fastest model. Then, for each bigger model in your hierarchy, you flip a coin. But this coin is super biased. It almost always lands on tails.
Only on the super rare chance it lands heads do you wake up that bigger model just to calculate a tiny correction. Because you're almost always using the cheap model, your average cost stays incredibly low. But because you get those rare, high-quality corrections, your final image has the accuracy of your best model. It's the best of both worlds. The implication here is absolutely staggering. This quote from the paper says it all. When you're in that HTMC regime we talked about, this method lets you solve the entire multi-step generation process for basically the same cost as running your biggest, best model just one time. It's like it makes the cost of taking all those steps just disappear.
I know, that sounds almost too good to be true. It's a beautiful theory for sure, but does it actually work in the real world? Let's get to the proof and check out the results.
This graph right here is the money shot. Let me walk you through it. On the vertical axis, we have error, so lower is better. On the horizontal axis, we have time, so more to the left is better. That means the sweet spot, the place you want to be, is the bottom left corner. The solid lines show the traditional method. You can see the trade-off, right? To get less error, you have to spend more time. But now, look at those blue dots. That's the MLEM method. They are consistently lower and further to the left. They are achieving a better result with less error in way less time. It's a slam dunk. So what's the bottom line here? When they measured it for the exact same level of image quality, the researchers saw a solid 4 times speed up. That means generating the same image in a quarter of the time. That's not a small tweak. That is a massive, practical leap forward.
And what's really cool is how versatile this is. On the left, you see the results for standard diffusion models, what we call DDPMs, and the speed up is huge. But on the right, you see the results for DDIMs, which are already a faster, more optimized type of model. And even there, the MLEM method still gives a clear advantage. So it can make slow models fast, and it can make fast models even faster.
So, let's step back for a second. A 4x speedup is awesome, don't get me wrong. But the real takeaway from this work is so much bigger. This really points to a whole new way of thinking about how we scale generative AI. And here is the absolute kicker. This isn't just a one-time speedup, it's a polynomial one. Remember that old scaling law with the 1 plus gamma in the exponent? This method basically just snips off that pesky +1. What that means is the performance gap between the old way and this new way is only going to get wider as models get bigger. So a 4x speedup on a small research model could easily become a 10x or even 20x speedup on the enormous models that the big AI labs are building. The bigger you go, the more you save.
And that leaves us with this final kind of mind-bending question. We've always assumed that progress in AI meant finding easier problems or simpler approaches. This research just turns that whole idea on its head. It shows that by correctly identifying and actually embracing the hardness of a problem, we can unlock speedups we never thought were possible. It really makes you wonder, what other unbreakable limits in AI are just waiting for us to find the right paradoxical key?